Okay. This is up close and personal with the rough diamond that I have magically made clear. Mm-hmm. Now, these are planes of cleavage inside the crystal structure. They're known as flaws in the diamond world, and I don't think so, but that's what they would be called if people tried to cut one of these into a gemstone, and they would find that my little crystal here is deeply flawed. It has no commercial value as a bazillion-dollar gemstone, but its real value is the fact that it's a piece of carbon that's so hard you can't break it. And this one happens to be tapered. And what I need is an axle for a high-speed Tesla turbine, and with bearings made out of and parts, structural parts made out of diamond. Balanced between two diamonds and spinning perfectly balanced. And what I would have is something that spins 6 different viewpoints round and around and around and around and around. Really fast. And so I think the electrons are probably carbon-14, creating beta emission in diamonds. is something that all carbon does, and it happens in this kind of carbon. This is plastic, and when I hit it with my blue laser, it fluoresces just like diamond. How about that? Because it's got the same stuff in it. It's got carbon in it. And carbon it comes in 3 flavors. Carbon 12, carbon 13, and carbon 14, depending on the number of neutrons in the nucleus. And ideally, it's carbon 13 in diamonds because it mimics the same cubic hexagonal symmetry within the nucleus of the atom. And so it continues the fractal self-similarity all the way down to the smallest of small. And carbon, the unit cell of a cubic hexagonal arrangement is 6 atoms surrounding each atom. Okay, so right in the middle, and then 1, and then 6 around the outside. And it forms 6, like, triangles that fit together. Bum, bum, bum. And those triangles, what they are is mirror images of each other. And that mirror symmetry is carried back and forth and across. And it's not random at all. Not random at all. It is indeed the way stuff fits together. And carbon atoms are all the same size. So they line up with each other in perfect little rows and columns, and they form when molten rock is cooling, and it cools down to 3,800 degrees Celsius. It's very hot. It's the first thing that precipitates out of the melt. And it's what begins cooling. It's like precipitation carries the energy of the melt with it, carries the heat away. And that's what happens. This carbon begins to precipitate out. The melt cools down even further, and aluminum oxide begins to form. And they form together concurrently. And the mountains that I live in are just about solid aluminum oxide. They are tremendously cool looking mountains when you look at them from Google Earth. I thought at first that they were just metamorphic granite and what we call schist or schist. And schist is like layers that have been stretched. And it turns out they're not like layer after layer and year after year. It's a crystal structure, and those are called planes of cleavage. Those are planes of cleavage. And that's what those layers are, and what they mean. They don't mean millions of years. What they mean is a structure that has rows and columns, because the individual bits and pieces are all about the same size. And this is gold platinum alloy, so it's solid gold platinum alloy. And it's a molecular joining. It's not little bits of gold and little bits of platinum. It's gold platinum alloy in a molecule. There's a gold atom and a platinum atom. Actually, 13 of them in various combinations. So the mixture can be more gold rich or more platinum rich, depending on what's there at the time. And that's what these layers are, is as the melt cooled down, it left different layers of stuff as it precipitated out. And they're metals. Those are all metal. The whole thing is a solid piece of metal. It has double covalent bonds. Double covalent bonds. People say, oh, it's metamorphic. It's been squeezed together. Well, it has too. You can see squeezed and moved. There's some movement across here, and you can see how this got pushed across the surface, and so you can imagine this in the ground, right? It's in a crack in the ground, and that crack is moving because the ground is cracking, splitting, and moving against itself. The stuff over there is going that way, and the stuff on the other side's going back the other way. And it met right here, and this is where the rubber meets the road, so to speak, in fault lines. And that's what we're looking at. Not millions of years. Worse luck, huh? And crystals actually form fairly quickly. So this was something else before it got squeezed. And you can see it got squeezed. But that's what those are. Those are planes of cleavage. So we're learning things today.